Hello everyone. Today we are going to continue our study of rational functions, and today we'll be looking at simple rational functions. And we might actually spend 2 days on this. I kind of breaks my heart a little bit that because of this timing, that we don't have, we have to kind of break things up, and it's going to spread things out and slow things down, and you're not going to get as much as teaching as I wanted to try and get you, but we'll just push forward because I also don't want to go too fast too much and have you guys overwhelm yourselves at home and stuff like that. So I don't know, we'll figure some stuff out. I might start supplementing towards the end of the year for people that want to kind of like move further, just to be more prepared. So anyway, we'll go with what we got right here. Okay, so we're probably going to spend 2 days here graphing simple rational functions, and then 2 days graphing more complicated rational functions as well. Okay, so we already talked about adding, subtracting, multiplying, and dividing rational functions. Remember, rational functions are just functions that can be written in the form a of x over b of x, where a and b are both just polynomials. Okay. Now when it comes to graphing, though, we're going to go back to that parent function idea, and our parent function for a simple rational function is f of x equals 1 over x. Okay, the first thing we'll talk about here is the domain. Okay, so what would the domain of this function be? Okay, and I challenge you to try and answer this without a graphing calculator. Just look at it. Are there any x values here that would cause problems? And the x value of 0, and why? Because it would cause us to divide by 0, which would make the function undefined. Okay, and we'll look a little more deeper into that today about why that's a problem, like what that means to be undefined and stuff like that. So you can list your domain as something like x not equal to 0. However, I really want you to be comfortable using interval notation here. And so in an interval, it would be negative infinity to 0, excluding the 0, and then draw the u for union, and then starting back at the 0 and going to positive like that. So this is the appropriate domain, okay? This is good, those excluded values that we talked about when we were adding and subtracting, multiplying, and dividing rational functions. But I want you to be able to list it as an interval too. Okay, and we'll get more practice of that as we go today, tomorrow, and 2 days after that. All right, so let's also talk about next end behavior. I know we're gonna skip the range for right now. We'll come back to it at the end, but we're gonna talk about end behavior. Okay, specifically, we want to know what happens as x goes to infinity. That means as we go really, really far to the right. Okay, and also what happens as x goes to negative infinity. That means what happens as we go really, really far to the left. This idea of x approaching something, okay, this idea is known as a limit. Okay, this is going to be fundamental to calculus. For those of you that have plans to move on to calculus or want to eventually get to calculus or thinking about calculus and kind of thing, the idea of evaluating what happens to a function, what the value of a function approaches, that is what the y values approach as x approaches a certain quantity. That's a limit, okay, because we're not actually getting to it, we're just approaching, right, which is a little bit of a fuzzier concept, but sometimes it's exactly the same as equality, but sometimes it's a little bit different. Anyway, that's what end behavior is. It's a limit. We're just approaching infinity or approaching a negative infinity, okay, in either case here. So one way to evaluate a limit is by using a numeric evaluation, which is sometimes we can just, that's as simple as using a table. So how can we kind of like mimic x approaching infinity? What does it really mean for x to approach infinity? So the idea is that x should get bigger and bigger and bigger, right? So how do we show x getting bigger and bigger and bigger? Well, you just type in larger numbers for x. We could do like 100, 1,000, and I can jump to like 1,000,000 here. Just get like really large numbers for x, and we'll see what do our function values approach then as we get really, really big. Okay, so let's go to our graphing calculator here. I already have 1 over x typed, and yeah, so I already have x typed in. 1 over x there, okay? I'm going to change if I go to my table right now, okay, you can see that it's like automatically set up, just count by ones, and that's going to take me forever to scroll there. So I'm going to change second window to table setup. I'm going to change my table setup from independent variable, which is the x variable. Instead of having it automatically fill it in, I'm going to have it ask me. And then we'll go back to y equals here. Oops, sorry, no, back to the table is what I need to do. It's blank. It's waiting for me to type stuff in. So I think we did, what, 100, and then 1,000. Oops, that's 10,000. And then 1,000,000. Okay. And that 1e negative 6 is just scientific notation. That's 1 times 10 to the negative 6. So it's like point,
0, 0, 0, 0, 5 zeros, and then a 1. I don't know if I said 5 zeros there, but you get the idea. Okay, so you can see that we go from 0.01 to 0.001 to 0.000001. Okay. Okay, so what's happening here? What's going to happen as you continue to get large here? What's going to happen to this value? What number is this function value approaching here? Well, it's approaching 0. Okay, so as x approaches infinity, f of x is approaching 0. Okay, let's see what happens as x approaches negative infinity. Okay, maybe we'll get something different. So let's try negative 100, negative 1,000, negative 1 million. Again, we'll go back to our graphing calculator here. Okay, and I'll just change all these to be negative 100, negative, oh, well, it ate my input, and now I'm just messing up here. Okay, and then negative 1 million. And look at that, we get the same kind of answers here. It's just the sign negative now, so negative 0.01, negative 0.001, negative 0.00. Oh, I didn't put enough zeros for this last one here, did I? 1, 2, 3, 4, 5, 6. Yeah, okay. 0.00001, like that. Okay, there we go. And what is this approaching? Well, it's negative, so it might be a little bit harder for you to imagine here, but negative 0.01, negative 0.001, negative 0.0001, what are we approaching here as these values get smaller and smaller? We're approaching 0 here as well. Okay, so as we go really, really far to the right, as we go really, really far to the left, both are approaching 0. Interesting. Normally, our end behavior is infinity or negative infinity, but this function goes to 0. What that indicates, too, is that we have something called a horizontal asymptote. Okay, since our end behavior approaches a number, okay, and that number is 0, we'll say that we have a horizontal asymptote at y equals 0. Okay, a horizontal asymptote kind of provides like a little bit of like a guideline or like a guidance as far as like our end behavior and stuff like that. And you'll kind of see it show up here if we get to it in the function when I graph it here at the end. All right. One other thing I want to look at too is the behavior around x equals 0. We already established that 0 is excluded from our domain, right, because that would make us undefined. But let's see what's happening, again, using this idea of limit, right, approaching a value to try and study it better. So in this case, we want x to approach 0. So what are ways to approach 0? Well, 0 has a negative side and a positive side. So we kind of like approached here too. For example, this f of x, right, when we increased our numbers right here, we were approaching 0, but only from one side of 0, right? It was from the positive side. If you want to actually indicate that, you can by putting a little plus sign there up in the exponent spot. Here, we are also approaching 0, right? But we were approaching 0 only from one side. It was from the negative side, or from the smaller side. And so we're going to put a little negative sign up in there in the exponent, just to kind of indicate that it's only on one side of 0, not both sides of 0. Right? As we approached infinity from this side, or from positive infinity, we were approaching 0 from the positive side. As we approached negative infinity here, we were approaching 0 from the left-hand side. Okay, and again, that left-hand, right-hand side stuff, if that's confusing, don't worry about it too much right now. It'll be something that shows up later in calculus, if you decide to take it. So we're going to do the same thing here. We're going to approach x, we're going to approach 0 with x, but from the negative direction. So in other words, we're going to put a little negative sign up in there like that. Okay, so what are values that are close to 0 but in the negative direction? We could try like negative 1, that's close to 0, but then what's closer to 0? Well, negative 0.1, and then negative 0.01, and so on and so forth. Okay, and let's see what happens here. Okay, so I'll clear these out. Actually, you know what, I'm not going to do it. So negative 1, negative 0.1, negative 0.01, negative 0.001. And I'll do like negative 0.000001 like that too, just so you guys can see. Okay, what's happening to our y values? Well, we went from negative 1 to negative 10 to negative 100 to negative 1,000 to negative 1 times 10 to the 9th. So these negative values are getting really, really big. In fact, it seems like the closer we get to 0, the closer these x values get to 0 from the left-hand side. Oh dear, I hit the search button. the closer these y values get to negative infinity. Okay, so as x approaches 0 from the left-hand side here, x values, the function values approach negative infinity, which is where we get that idea of undefined from, right? If you try and plug 0 in here, you're going to get infinity, right? Or negative infinity, I guess, depending on what side there. And that's undefined, right? It doesn't have a value, it just kind of keeps going. So we can't say infinity is an answer there, so we just say the answer is undefined when you plug in infinity in. The same thing is going to happen here if I try approaching 0 from the positive side. It's like 1, 0.1 is a little bit closer to 0, 0.01, 0.001, you get the idea. Okay, if I put in 1, I get 1. If I put in 0.1, I get 10. If I put in 0.01, I get 100. If I put in 0.001, I get 1,000. And so again, what's happening here? As these x values get closer and closer to 0, these y values get closer and closer to positive infinity. So as we approach 0 from the positive side of 0, right, these numbers are positive, greater than 0, the function value there goes to positive infinity. Okay, so you'll notice we're approaching two different infinities as well. So that's another kind of reason why at 0 we're undefined. From the left-hand side, we're going to negative infinity. From the right-hand side, we're going to positive infinity. And so it's like jumps. All right, so let's see what an actual graph of this thing looks like. Oh, well, by the way, sorry. Since we have this behavior here of our function approaching infinity as we get closer and closer to 0, we say that we have a vertical asymptote. At 0. Okay, vertical asymptotes and horizontal asymptotes both have this kind of like boundary behavior to them, but vertical asymptotes are special in that your graph will never cross a vertical asymptote. Okay, you could potentially cross a horizontal asymptote, but you will never cross a vertical asymptote. Okay, so let's take a look at what this looks like then. All right, in our table here, I'll just go ahead and fill this in. This is negative 1/2, this is negative 1, this is negative 2. Oops, not 0. We just said it was undefined, right? Okay, if I put 1/2 in the function here, I get 2. If I put 1 in, I get 1. If I put 2 in, I get 1/2. And we'll plot these points over here. So I'm going to put in my vertical asymptote. To indicate a vertical asymptote, you just draw a vertical line, like so. You can even say, you know, VA if you want to, x equals 0. I'll also draw in the horizontal asymptote here, so it's a dotted line as well. But this is a horizontal asymptote at y equals 0. And these are important behaviors to be able to identify as well. And we'll talk more about these, you know, as we progress here for today and tomorrow and, you know, the 2 days after too. So don't sweat too much if you're kind of having trouble with these. All right, finally we'll plot these points. So negative 2, negative 1/2, negative 1, negative 1, negative 1/2, oops, 2. Well, I lost my line there. Okay, there we go. And then, so that's going to create like this kind of curve right here. Okay, you see I'm hugging that asymptote, but I am not going to cross it. All right, and then over here, oops, I plotted those completely wrong. I erased my line again. Okay, here I should have done, it was negative 2, negative 1/2, so that's like right here, and then negative 1, negative 1, and negative 1/2, negative 2, like that. Sorry, so this is what the graph should look like, something like this, and I can't see my point. My hand's blocking me. There we go. Okay, so again, you're going to approach the asymptotes, but don't cross them in these cases, okay? And then for the other one too, so let's see here, 1/2, 2, 1, 1, 2, 1/2, and again, just kind of like that. Okay, so yes, the graph has two pieces to it. Both of these pieces right here are integral. Okay, it's both part of the graph. Yes, they're broken up. This function is not continuous, right? There's a lot of weird stuff going on here with this function that we haven't seen before. But speaking of stuff we have seen before, of course, we always have our transformations. So you can see we have our vertical stretch. Same thing as before. If a is greater than 1, absolute value is greater than 1, we stretch it. If a is between 0 and 1, the absolute value is between 0 and 1, we shrink it. If a is negative, we reflect over the x-axis. H is going to shift left and right, and just like that normal way it would, if you see an x minus a positive number, that means you're really shifting right. If you see x minus a negative number or x plus a number, it means you're shifting left. And then k is, you know, shifting up and down, positive k up, negative k down. Okay, so we'll talk more about this as we go. I'll give you guys a brief homework assignment. Thanks for sticking with me here. There's some crazy concepts. If you have further questions or if you're interested in calculus and want to ask me some further questions about the limit stuff, please feel free. Catch you guys later.